Hello everyone, I'm going to take you through my SML assignment where I analyzed a high-dimensional dataset for cancer classification. So the main goal was to understand the structure of the dataset, identify which variables has more meaningful information that will help us to distinguish between cancer and non-cancer samples. So the dataset contains 79 observations and 501 gene expression variables. So I realized that my dataset was a high-dimensional biological dataset where the number of predictors were more than the number of gene expression variables. So the distribution of my response variables showed that the classification models are unlikely to achieve good performance simply by predicting the majority class. And the accuracy will generally reflect the ability to learn more meaningful patterns from the data. So I used also a histogram by selecting nine strongest variables where their widespread and structure shapes suggest that they capture meaningful biological differences between individuals, and this will explain that large crucial statistics confirms that the variable is individually informative for distinguishing between cancer and non-cancer subjects. I also use comparative box plots for the 9 powerful predictors, and here I observed that the median expression levels shifts noticeably between the cancer and non-cancer variables. I also repeated this for the comparative box plot for the 9 weakest variables, and I observed that the box plots lie on top of each other, almost lies on top of each other, and they carry little predictive information, as you can see. After that, I checked for the correlation of predictors, where I observed that there is a strong multicollinearity between the variables, indicating strong dependence between the variables. And again, the composition of this correlation matrix shows that the matrix is nearly singular, and this confirms that there is a strong multicollinearity between the variables. The comparative RC curves shows that among the tree-based models, the unimproved tree achieves the strong apparent performances, with its curve closest to the top left corner, indicating very high sensitivity even at a low false positive rate. However, this is likely to reflect overfitting since training and testing are performed on the same data. And for the plot of the comparative box plots, here the plots, this pattern reflects the effect of model complexity. More flexible models are more stable, while the regularized models generalize more consistently across different data splits. And for the ANOVA results indicate that a statistically significant difference in mean test error across the learning machine, as shown from the large f-value and very simple p-value. This confirms that the choice of the model has a meaningful impact on the generalization performance.